In this video, we're going to wrap up our series on type checking with a discussion of how to recover from type errors. So as with all the other front-end phases, like lexing and parsing, it's important to recover from errors that happen during type checking. But unlike parsing, it's much easier to recover from errors in the type checker because we already have the abstract syntax tree. And so there's no need to skip over portions of the code as we did in parsing before we even knew what the structure of the program was. The problem, though, is what type should we assign to an expression that has no legitimate type? The type checker works by structural induction, and it can't just get stuck. So if we find some sub-expression that has no type that we can meaningfully give it, we still have to do something with it so that we can type check all the expressions that surround it. One possibility is to simply assign the type object as the type of any ill-typed expression. And the intuition here is that even if we couldn't figure out what the type of the expression was supposed to be, certainly it was something that was a subtype of object, and so it is certainly safe to assign any expression the type object. So let's consider what happens with this strategy in a simple piece of code. So here we have a little code fragment, and we'll just assume here that x is undefined, that actually there's a bug in this code, and that's that x has no binding, so there's no type anywhere for x. So what happens when we type check this? Well, we're going to recursively walk down the abstract syntax tree. Eventually we'll get to the leaves, and we'll try to type check x, and then we'll discover that there is no type for x anywhere. And that will result in an error message saying that x is undefined. And then in order to proceed with type checking, in order to recover, we'll have to assign x a type. And so we'll just assume that x has type object because that's our recovery strategy. And now we'll continue to type check as we walk up the abstract syntax tree, and the next thing we'll try to do is a type check this plus operation. And we'll see that we're adding something of type object to an integer. And of course, plus doesn't work on things of type object. So we'll get an error, something like plus applied to an object. And then we'll have to decide, now that we couldn't type check this plus, what the type is of x plus 2, so this whole sub-expression. And of course, our recovery strategy is to say, well, that also has type object. And now the next thing up in the abstract syntax tree is this initialization assignment. Here we're assigning y the result of this expression. But we couldn't type check this expression, so it has type object. And now the type checker sees that we're assigning something of type object to something of type int. And we get yet a third error saying that we have a bad assignment of some kind. So the nut of the problem here is that this simple recovery strategy works. We do recover, we continue type checking, but a single error leads potentially to lots of other errors. So this is a workable solution. It achieves the goal of recovering, but in general it will lead to cascading errors. Once you have one type error, that type error will just cause many more because not very many things can be done with something of type object, and probably the code was written assuming some more specific type. And these errors will just propagate up the abstract syntax tree until some point, and it just result in multiple errors. Another possibility is to introduce a new type, no type, that is specifically for use with ill-typed expressions. And no type is very special. It's not a type that's available to the programmer. It's only available to the compiler, and it's just there for error recovery and type checking. And the special property of no type is that it's going to be a subtype of every other type. So if you remember, object was the opposite. Object is a supertype of every type, and that had the bad property that there are very few methods defined on object, and so if you plug in type object where you expected some other type, probably it's not going to type check. So we can fix that problem by introducing no type, and no type will have the special property that every operation is defined for no type, and furthermore, we'll say that it produces no type as a result. So any operation in the language that takes an argument of type no type, it will produce a result of type no type. So the no types will propagate. And now let's take a look at our same code fragment, and let's work through what happens if we use no type. So Again, we walk down the abstract syntax tree, we get to this leaf x, we see that x is undefined. We produce an error saying x is undefined. And then we have to assign a type to x, and so we say, well, x has type no type. And now we consider the plus operation. And now plus is taking an argument of type no type and an integer, and this is fine. We're not going to produce any errors. That's considered to be well typed. And the result is also of type no type. And now we're doing an assignment. And no type is compatible with int. No type is a subtype of int. So this assignment is also type correct. And we don't produce any error at that stage either. And so you can see that what happens here is that the no types propagate up the abstract syntax tree just like the object types did before. But since no type is a special type that's used only for error recovery, we can distinguish it from all the other regular types, and we know that we shouldn't print out an error message after the first one is produced. So a real compiler, a production compiler, would use something like no type for error recovery. But there is an implementation issue with no type, and in particular, the fact that no type is a subtype of every other class means that the class hierarchy is no longer a tree. If you think about it, you have object at the top, and then you have this tree structure branching out, but then no type is a subtype of everything. So no type becomes a bottom element, and this is now a DAG and not a tree, and that makes it just slightly harder to implement. Instead of being able to just have tree algorithms, now you have to either have a special case for no type or do something more general. And this is just enough extra hassle that I personally don't think it's worth doing for the course project, and I recommend that you use the object solution. And we just live with the propagating or compounding errors that produces.